So, let us delve into the basics of probability and random processes as required for this course. So, I am not going to go into details of probability and random processes because it is a separate course in itself, but I am just going to cover the material just for your understanding so that you are comfortable through the rest of the course. Okay. So, let us first understand what a probability space is, and for which we have to formally get into the details. So, let us briefly understand what a probability space is. For this purpose, we need to understand the definitions behind fields and sigma fields. This is more in a modern set theoretic setup. One can think about the combinatorial way of looking into probability, but the modern notion is a set theoretic approach. So, therefore, I will cover this from the set theoretic approach, just basics, so that you are comfortable seeing through this material. Okay. So, now let us start with our understanding of what fields are, right. Now, consider a universal set omega and a collection of subsets of omega. You have a universal set and we are looking into a collection of subsets of omega. Let E f so on denote the subsets in this collection. Now, this collection of subsets forms a field script m if the following properties hold. So, what are the properties? So, the null set belongs to the field and the universal set belongs to the field, that is null set and universal set are part of the field. Second, if the subset E belongs to the field M and subset F belongs to the field M, then the union of E and F belongs to the field, and so is the intersection of E and F that belongs to the field. The other property is if E belongs to the field, then E complement belongs to the field. Now, these are the properties. A sigma field F is a field that is closed under any countable set of unions intersections and combinations of these unions and intersections. That is, if E1, E2 and so on till En, maybe you can extend this, belong to the field. I mean, I said we can extend this E1, E2 so on En, because you can have infinite such sets. So, if they belong to the field, so do the union of all these sets and the intersections. So, a set of elements in at least one of EI, this would be the intersection, and here is a set of all elements in every EI, right. So, this implies set of all elements in at least one EI. This is set of all elements in every EI. Now, there is this notion of countability that I introduced, and what we mean as follows. A set S is called countable if there is an injective function f from the set S to the set of natural numbers, which is 0, 1, 2, so on. So, I think you have to ponder some things here. The set of rational numbers are countably infinite, whereas a set of real numbers are uncountably infinite. So, the details of the proof of this countably infinite and uncountably infinite, you can get into the details by looking into any analysis book, and you may get some idea how to go about these. Okay. Now, let us go a little further. Consider an experiment given by script H with a sample description space, with a sample description space omega. If omega has a countable number of elements, then every subset of omega may be assigned a probability consistent with the axioms such that for every event E belonging to the field f script f, the following hold: 1, the probability of the event should be greater than or equal to 0. Now, we are assigning some metric, some measure to this, right. So, probability of the event has to be greater than or equal to 0, probability of omega, which is your universal set, has to be 1, and probability of E union F equals probability of E plus probability of F if the probability of E intersection F is 0. Right. Now, the class of all subsets make up a sigma field, and each subset is an event. So, here we are defining first what an event is in terms of subsets, and that is an important distinction that we need to make, right. When omega is not countable is an important point, and when can you have something which is not countable, that is omega is possibly the real line. Not every subset of omega can be assigned a probability consistent with the above axioms. We listed the axioms in the previous slide. Okay. So, only those subsets for which probability can be assigned are called events. Now, the collection of those subsets is smaller than the collection of all possible subsets that one can define on omega, and this smaller collection is called a sigma field. It is also known as a Borel field. So, the three objects omega, the field and the probability measure form a probability space, right. Just to recall, omega is the sample description space, F is the field, and we have seen what properties a field must satisfy, and then this is the probability measure consistent to the axioms which we described. So, when somebody talks about probability space, I think you have to understand that we mean that we are referring to these three objects which are part of this space, that is the sample description space, the field and the probability measure. This is an important concept in the context of the modern set theoretic framework for probability, and often you will require this notion in your research or in your higher understanding, right. Let us just revisit in this context the simple coin toss experiment and see how we can relate these objects. So, suppose we do a fair coin toss once, right. That means we have a collection of two subsets which are the head and the tail outside of the null set and the universal set. So, the universal set is basically comprises of the head and the tail. The sigma field of events consists of the following sets. It could be a head, it could be a tail, it could be a null set, it could be the universal set. See the distinction between the probability description space and the sigma field. And then we have the probability measure. The probability of measure is basically a measure on this sigma field of events, right. So, the probability of the head, since it is a fair coin toss, it is 1/2, and probability of tail is also 1/2, probability of a null set is the 0, probability of the universal set is 1. So, this gives you a sort of an idea what we are referring to. So, this is our object omega, this is our object, this is the field, this is the probability measure P, and this is the probability space for a fair coin toss experiment. Okay. Now, let us recall a few other basics and we will try to recap a few things. Probability of the joint occurrence of two events A and B is given by probability of A and B. You have to read this as probability of A and B. This is basically the joint probability of events A and B. So, an example is A is an event when it rains, B is an event when it is sunny, C could be a joint event when it rains and is sunny. Probably you might sense a rainbow, right. So, probability of this event C is the joint of A and B, probability of the occurrence of event A and B, right, and that is what we mean. This is basically an intersection. Now, one can think about how to do this from a combinatorial way. That means you can count the number of events when it rains, count the number of events when it is sunny, count the number of events when it is raining and is sunny over the number of experiments that you conduct, right, and then you can bring this notion of what the probability measure has to be. So, this is some basics. Let us also recall a few definitions. Independence. Two events A and B are statistically independent if and only if probability of A and B, that is joint occurrence of probabilities, the joint occurrence of events A and B, the probability of the joint occurrence of the events A and B can be decomposed as probability of A times probability of B. There is also a notion of mutually exclusive property. So, what it means is occurrence of one implies non-occurrence of the other. So, in this case probability, the joint probability of A and B is 0, and therefore, the probability of A union B is probability of A plus probability of B, right. And then we should also know the Bayes theorem. I think all of you would have seen this from your high school, but just to recap, if AI's I equals 1 to n be a subset, I would say be a set of disjoint and exhaustive events over a probability space P, some script P here, then the union over all these AIs is omega. Let us assume that AI intersection AJ is null for I not equal to j, that is take two events and they do not jointly occur, it is a null. Then for any event B over this probability space P, the probability of AJ given this event B is probability of B given AJ times probability of AJ divided by summation I going from 1 to n probability of B given AI times probability of AI. So, this is basically probability of B, and we have expressed the joint of probability of AJ and B in two different ways using the Bayes theorem. The proof is pretty straightforward from the basic definition of conditional probability, and I will leave this as sort of an exercise for you to ponder about. So, let us now get into the understanding of what probability distribution function is. This is also called the cumulative distribution function. The probability distribution function contains the information necessary to compute the probability of an event E for any event E in the Borel field of events. So, if you get into the mathematical notation, the probability distribution function is basically the probability over all zeta such that under the mapping x of zeta, you are looking at a collection of all zeta such that this mapping is less than or equal to some chosen x, right. So, this is given as the probability, the random variable over the event minus infinity to some small x, some chosen number. So, this is basically set of all outcomes zeta in the underlying sample space such that x of zeta assumes values less than some chosen small x, right. I give some small x and I want to figure out under the mapping x the set of all outcomes zeta such that x of zeta is less than or equal to that chosen quantity. Now, as you can see, the set of all zeta such that x of zeta is less than or equal to x is contained within omega, right, and this is a subset of outcomes that under the mapping x generates the set minus infinity to x. Now, we have a few properties for this probability distribution functions. I am just going to enumerate them. First, the probability distribution function evaluated at infinity is 1, f infinity of f x of minus infinity is 0. If I consider two quantities small x 1 less than or equal to small x 2, this implies that the probability distribution function evaluated at small x 1 is less than or equal to the probability distribution function evaluated at small x 2, right. This is basically the non decreasing property of the cumulative distribution function or the probability distribution function. Okay. Then there is a third property, capital F x of small x is continuous from the right, that is the probability distribution function is right continuous. What it means is capital F subscript capital X of x is basically limit as epsilon goes to 0 of the distribution function, probability distribution function evaluated at x plus epsilon slightly at epsilon greater than 0. If the distribution function is discontinuous at a point say x naught, then the distribution function at x naught will be taken to mean the value of the probability distribution function immediately to the right of x naught. So, if at that point x naught, if it is discontinuous, then you will consider the value of the probability distribution function immediately to the right of the point x naught, and that is why we have the right continuous property here. Now, let us consider a simple example. Suppose x is a binomial random variable, then probability that x equals some k is given by n choose k p power k 1 minus p power n minus k. This is the probability mass function, and the probability distribution function is given by this quantity, where you basically look at the floor of x, sum all the masses from k equals 0 to a chosen floor of x. Now, how should this look like? If you just evaluate for n equals 3, right, so when k equals 0 is 0, let us plot this probability distribution function, right. It has to, let us say we have 3 values 0, 1, 2 and 3, right. At 3 definitely this has to be 1, because you do not have anything more than 3. So, therefore, this has to be 1, right. Let us assume that we accumulate the mass till 1, and that quantity is A1, and then there is a discontinuity, then we accumulate a mass at 2, and that is A2, and then we a mass at 1, a mass at 2, and basically after 3 it is basically a constant, right. So, if you were to evaluate probability that 1.5 is less than x less than 3. So, x is some number given to you, then this is basically the distribution. If you want to evaluate this probability, this is the distribution at 3. You assume slightly, though it is less than 3, you assume the accumulation at 3 minus the probability that x equals 3 minus the accumulation or the probability distribution function evaluated at the point 1.5, because you have to subtract that mass here. So, this would be basically 1 minus probability that x equals 3 is what you can compute, minus this point f x of 1.5 is this quantity A2 reading off from this label here. This is how you would actually compute the probability distribution function. So, I gave you the probability mass function here because I mean this is basically the probability that x takes a certain value. This may not be so direct and straightforward when we look at continuous random variables, because first we start with the probability distribution function, and if the distribution function is continuous and differentiable, then we can basically get the probability density function. So, let me define what the probability density function is. If the probability distribution function is continuous and differentiable, then the density function is basically a derivative of the probability distribution function, and we assume that the derivative exists, so therefore we can take the derivative. So, the properties for the probability density function are as follows. 1, the density function, probability density function is non-negative, right. It makes no sense to say that the mass, probability mass function or the density function is negative, right. There is no meaning to that negative quantity there, because it is a derivative of the distribution function. So, there is no meaning to this mass which is negative. So, it is non-negative, then it integrates, the density should integrate to 1, right. Why? Because you evaluate, how do you compute this quantity? This is basically from the probability distribution function, it is f(x) of infinity minus f(x) of minus infinity, which is basically 1 minus 0, right, and that is why you get it as 1. Now, the distribution function is linked to the density function. If you integrate the density function from minus infinity to a point x, some constant x, then you get the distribution, probability distribution function evaluated at x. This is giving you the probability that the random variable x, capital X, is less than or equal to some constant small x. Now, if you want to compute the difference in the probability distribution functions evaluated at 2 points x1 and x2, which is giving you the probability essentially that the random variable x is between x2 and x1, that can be obtained by integrating the probability density function between limits x1 and x2. So, these are some basic properties. You would have seen all of these, but now in the context of sets etc., you will be able to better appreciate what is really happening here. Okay, and if you think about the probability density function, so the probability for continuous random variables, probability at a certain point is essentially 0, right. I mean it makes sense, because if you shrink this integral, if x1 and x2 coincide, or x2 is just epsilon from x1, and if you just collapse that interval, basically that gives you 0 for the probability, and therefore the probability for a continuous random variable, the probability that the random variable takes a certain value is basically 0, and that should be obvious. So, with this I will sort of discuss some subtleties between continuous, discrete and mixed random variables. So, random variables can be continuous, they could be discrete, and they could be mixed. So, examples: The Gaussian random variable is one example for a continuous random variable. Then we have the for example, if you look at the binomial distribution, that is an example of a discrete random variable. Sometimes you can have a mixture of continuous and discrete random variables. So, a mixed random variable, I can give you an example. So, for a mixed random variable, if you look at the sketch of the probability distribution function, I can have jumps indicating it is discrete at some points, and then I may have something which is continuous, right, and of course this has to integrate to 1, right. So, this is an example for a mixed random variable. So, for a continuous random variable, you can just imagine that the PDF is basically continuous. For the discrete case, we have seen an example of a staircase function is where things are discrete. Okay. Now, we will try to work out a simple example considering a mixed random variable. Suppose the PDF of a mixed random variable is given as follows. This is uniform from 0 to 5. There is a height, some k that I do not know, right. At 2, I have a mass, an impulse, which is height 0.2. This is delta x minus 2, and at 4, I have another impulse which is 0.3 delta x minus 4. Now, under any circumstance, the density must integrate to 1, right. So, since density must integrate to 1, so let us look at the integration here. So, this is area of this rectangle, which is 5k, 5 is the base and k is the height, 5 times k, plus you have a mass of 0.2 at 2, an additional mass of 0.2 and another mass of 0.3 at x equals 4. So, this must sum to 1. So, this implies k is 0.5 upon 5, which is 0.1. And if you sketch the PDF, that will be pretty interesting, because let us sketch this. Sketch of the probability distribution function. So, between 0 and 2, right, I have a ramp, because I am just integrating this this rectangle here, right. So, that I am with a slope of 0.1, I just have a ramp here, and I accumulate a mass of 0.2 here on the y axis. Then at 0.2 I have a jump of 0.2, so I basically accumulate a mass here of 0.2, right. I think I can indicate this jump perhaps through dotted lines. So, I accumulate a jump of 0.2 at x equals 2. So, I go to 0.4. Now, between 2 and 4 I do not have any impulse. So, I basically keep integrating it till I accumulate a mass of 0.6, and at 4 I have an impulse with a mass of 0.3. So, I accumulate a mass of 0.3 here, and I get to this point which is 0.9, and after 4, between 4 and 5, just immediately after 4 I just have a ramp with a slope of 0.1, and then I touch this is 1. Okay. So, this point is 5. So, this is a sketch of the probability distribution function. So, I think this gives you an idea. So, at these points it is discrete, and at these points it is continuous. Okay, this is continuous, and these 2 points are basically discrete. So, maybe I can put a green color here indicating it is discrete, and red color indicates it is continuous. So, this is a sketch of the probability distribution function for a mixed random variable. So, hopefully with these basics you may be able to understand and appreciate the subtle details when you actually look into the probability distribution functions and probability density functions, which will be useful for your analysis further during the course when you have to deal with these probabilities.